Thank you, Ken. You didn't mention that we used to have our offices across the hall from each other. And often we were teaching different sections of the same course. And I would teach his course when he had to go to town, he would teach my course. So it's my pleasure to give a talk here, finally to give this talk. This is not your usual Nobel laureate lecture. This is a lecture that's different. I've been calling it in my mind my Ring lectures. I should be giving a set of 4 lectures, just like Wagner's operatic drama series, The Ring. I haven't figured out how to give the last one, but I can tell you what the third one should be because I started working on it. The first one I gave on Friday, and the point I was trying to have there is because of tremendous advances in technology and future promise advances in technology, we've actually entered the area that John von Neumann named the singularity. It's actually started, and that's a time in which new technology discoveries come so quickly that human beings cannot respond to them. But more importantly, those new discoveries and technologies are at variance with human institutions and laws and so forth. And those will be swept away, and they will be swept away pretty soon. Usually it takes like a recession or a depression to start sweeping things away quickly. We have people working to disturb the world order, but those discoveries, if we kept the world order together, in 5 years would make us twice as wealthy as we are now. So it's in everyone's interest to try and keep the world order together, but to also adapt. And so one of the things, since I was talking to professors at this meeting, I didn't mention one of the human institutions that will be swept away is the university. Professors don't want to hear that because I know I was worried that online instruction and was going to affect teaching. Now, the teaching load was kind of hard, in another sense. It's clear that a lot of undergraduate courses had already taught. But the fact is, it was the reason they justified paying our salaries. Why, the same thing is going to happen here. And the university has to reinvent themselves by doing projects that you can't get with the other technology. So this is the example of a project that we can do as University HKUST that justifies continuing to get government money when the money is going to be cut back to all the other universities. There's going to be one university left in Hong Kong in 10 years. That's just to get you, to get your attention and get you concerned about it. Because this is one of there are 3 projects I can think of. This is one of the ones that the government and the population and the people in the university are all going to say is a good thing. Because it's going to provide for them much better health. It was not a medical thing. Medical is when things get broken. Health is when you're not sick and when you're living well and you're having a nice time and you feel good. So you want to be working towards the thing where you have health, right, until you have the problem where you have disease. Stem cell is the thing in the right direction. And 50 years ago, I started an effort where I applied physics against cancer. Okay. So the word against is very important because just before, a few years before that, I had to take college entrance exam, and one of the things we had to do was correct a essay that proved you could read and write. Okay. And the title of the thing was Crusade for Cancer. Okay, well, we're not crusading for cancer, we're crusading not to have cancer. So I'll mention one of the things that moved me into the stem cell business as the correct way to deal with cancer. So here we're going. This is the background. The only thing wrong with this background is there are people in it besides the patient. It really should be computers and machines doing 99% of the stuff, and the patients, the handlers of the patient are probably nurse practitioners. You can say all these good things about the future healthcare, where we should have a school of futuristic advanced healthcare and some medicine here as what the university is actually doing. Healthcare is going through a tremendous revolution due to the fact that when I was young, digital won out over analog. You might not know that, but when I was in college, My roommate worked part-time at Draper Lab, building analog computers to train the astronauts how to land on the moon. Because the digital computers were not good enough and fast enough. But analog computers could be made to do that. So, landing is not so simple when there's craters and boulders and stuff. And they had to train the astronauts how to do that, and they used analog computers those days. It wasn't much longer after that digital computers took it over and we started digitizing everything. A lot of anti-aging and healthful, longevity, personalized healthcare stuff. We'll come back to that hopefully in my next lecture. We have cellular genetic treatments. We have a deep understanding of cell functions and growth signals between cells. Something that I actually knew about indirectly when I was younger, but now understand in a much different way. We've got CRISPR, Cas9 technologies, so that we can do genetic interventions easily and cheaply. And there are more than 5,000 gene therapy trials listed by the National Institute of Health. There's only 1,000 diseases, so we're overkill here, except there's different modulations somewhere, so some be not. And there are more than 8,000 worldwide, and I'll show you some stuff. And we got robotic surgeons and robotic doctors and medical image readers, of which 2 out of the 3 have already kind of taken over the field. The third one, the doctors are resisting. So here's a slide that I was giving in talks some years ago. When your baby is born, you take the umbilical stem cells and you store them. And why is that? Well, because those are as close as you can get to the original stem cell, and you can, in principle, preserve them and take care of them. So that 50 years later, when there's something in you that needs fixing because you have something, you can go in there with those stem cells and fix it. Now, we've made a lot of progress in recent years, so we can take some adult cells that are not so advanced, they're quasi-stem cells, and you can try and use those to do that. That's how the 5,000 treatments are going on. And this just shows the concepts there. And this is an advertisement that I found 3 or 4 years later from a company in Hong Kong advertising how they will come to the hospital, get your baby's stem cell, take it to the stem cell treatment center where it gets all fixed up. That was fairly primitive, but this is what you do. And a number of people did that. And one of my colleagues will come back to later, I convinced to do that. His son is now almost 18. So this is also moderately old slide, 10 years old slide that I put in. How many diseases are treated by stem cells? Well, in 1988, it was 1, right? By 2007, it was 40. By 2017, it was 80. What's it going to be in 2 years? The answer is a lot. Right? And so that's unfortunate for most people in this room because they haven't got their blood stem cells. They've got to get their quasi-stem cells from other things. And we'll talk about what that is. Here's one of the things that I could find, but it's only good out to the year 2012 plus 1, right? That is the number of stem cell clinical trials going on as a function of year. What you can see is the exponential growth, and then is it rolling off the top or not rolling off the top? That's done in 2012, so you don't get the full curve of what's going on. And there's a whole bunch of stuff, mesenchymal stem cells. Usually when they're talking about that, they're talking about stuff taken from your bone marrow. Right? But there are other ways to get these kind of things. So not only can you get your umbilical stem cells if your parents were foresighted, you can do it now as a person. And so here's a more up-to-date version, right? It supposedly goes to 2025. There are stem cell activities going on, mostly in North America and Europe, and in China. And you can look at the various kinds of things they're doing. They're doing things, stem cell treatments for eyes. There are 4 different stem cell treatments for eyes that I know about. I'm looking at one of them. It's for macular degeneration. I may be getting that in this eye. I have to wait and see. The age one is one that happens, unfortunately, when you get older. So there's a lot of different kind of things that you can look at and see. And there's a hint that is rolling off, that we're not having the exponential growth in stem cell trials that we had 4 or 5 years ago. But that's a sign that they're transitioning into this next level. Is anybody in this room has stem cell treatment? It's funny, now when I run into people where I was doing other stuff, I've found already 4 people who had stem cell treatments. And one of them for knees that was miraculous, from somebody who was originally playing tennis and then went to pickleball. They had a wrist issue and a knees issue. So here's the global stem cell market forecast. Depends on what you're talking about it by Therapy. 19 billion last year, predicted to be 54 billion way out in 2033, which is 8 years away or something. It's still exponentially growing, and it's growing at a rate that's in the 27 to 28% per year. This is really fast. Okay? It's hard for people to try and understand what's going on. Now here's another ad from Hong Kong. I took this off their website page. Do you notice anything here? Well, a lot of it's about making your face look young. But there is stem cell storage, and there are some other treatments, but mostly it's about making people look young. And tells you what's important. But Hong Kong has got the oldest population in the world. There's a severe aging issue. But people still like to look nice, and a lot of people in Hong Kong are rich enough to afford this. And this is one I picked from a place in Mexico. This is an ad that they think people will respond to. That is, better hair, well, that's kind of like a better face, but not as obvious. Improved vision, that is. Eye aging is a very serious issue, especially if you have an aging population. Your immune system, well, this is good, this is different. Metabolism, right? Well, that's related to the immune system. The immune system. And you look at these things that they're advertising that they will give you stem cell treatments for. These are not just fly-by-night places. These are people who are running real stem cell organizations. They even tell you what they're going to do. They're going to do a consultation. They'll schedule treatment. And in some cases, if you're busy and rich and can't afford to go there, they will take the stem cell samples from you, fly it to their factory, produce the stem cell treatment for you. 21 days later or something, you come down, check into a first-class hotel, then you get injected, and you're watched for a couple days, and then you go home. That's it. No surgery, no anything. You just get that treatment. Well, that's kind of okay. It's not the best, but it's okay. Okay, here's another ad. Advertising the 10 benefits of cell therapy in Mexico. Okay. Well, they got a bunch of rich customers just north of the border, and they're not a bad place to go visit and so forth. Allogenic mesenchymal certified cells, but they're going to give you the stem cell treatments. What's the level of the market? And it's the reason I'm doing this is because this is going to be a joint progress between the university, private people who can make a lot of money, and the government who wants to provide healthcare to the people. And if you look, 2 years ago, it was 20 million. They're predicting that in 5 years, it will be 113 million or something like that. That's not very impressive, except it's in a country that a lot of people in the US consider backwards, and yet when you look at these facilities, they're quite amazing. There are a number of countries vying to be the low-cost stem cell provider. When you have a field that's growing exponentially, anybody that starts in a business in that will make money. After you reach a certain level, it turns out it's the low-cost, high-quality producers that have a great reputation that eventually take over. Some of you may not remember the way I do, but I can remember when personal computers started out like crazy. Some of you may remember this. And there were companies all over the place, and you never hear about Eagle Computer anymore. I remember that particular one because on the night they went public, one of the co-founders drove his Ferrari into a telephone pole at high speed, and that wasn't good. Right? But Dell Computer, Apple Computer, IBM, there's only like 4 computer companies really left in the US. There's some more in other places in the world. But the number of computer companies crashed down because there were certain people who provide a quality commoditized. You can see how the price depends on how much people think they're willing to pay. Compared to the US, where it costs 20 to 50,000 for such a treatment. Here you're looking at stuff that's running between $1,500 and $5,000, depending, unless it's some kind of special disease like hematopoietic stem cell therapy. That depends on what they think they can get out of the person. And there are a couple of other countries that are trying to do stuff in this, like Malaysia, but they're in Colombia, but they're not going to be big players in this market because they haven't got up the curve yet, I think. It requires some brilliant, very rich businessmen to come in and pull them up in the state. It's just an example of the kind of stuff that's actually going on now, and it's surprising nobody in here and nobody knows anybody who's got stem cell treatments because it's starting to happen quite a lot around the world. But you can see Thailand is going, it's looking towards having 6 billion by 2030. Exponential growth, right? That's what phases we're in. Well, what about China? Already, it was $1 billion last year. We think by 2030, it will be approaching 5 billion. That's serious money. That means there are serious players trying to figure out how to get in this market. I'm just trying to convince you that the people who want to make money want to be in this business, right? Because they can see it's something that's really the future. Okay, and worldwide, 27 billion. Because already in the United States and Europe, there are people doing medical tourism or getting treatments in those countries. Okay, so here's the geographic location of the clinical trials. Right? You can see there's a bunch in the US. And you know why some are here. There are certain places that are high biotech areas that have good hospitals and medical stuff, and high-tech industries. They have the base in which to be able to do that. You say that again here in Massachusetts, Maryland, you look at it and see. And again in Europe, there's a whole lot here because it was a big pharmaceutical holding them. And again, France doesn't want to be left behind. Surprisingly, Spain is coming up very big in this. So those are very serious areas. There will be that kind of activity here, but not so much in clinical trials, in actual treatments. There will still need to be some advances in the field. It's very early. It's like renewable energies. It's developed some, but compared to the internal combustion engine or drilling for oil, mining coal, those are really old technologies. We're talking about a new generation here. There will be new discovery. That's what universities can help with in a great way. Okay, don't forget your mitochondria. Turns out your mitochondria are responsible for somewhere around 45% of the effects of old age and shot. A big shot of sugar makes your mitochondria work extra hard. If you overtrain your mitochondria work extra hard, if you don't get enough, your mitochondria don't get rid of it. There's a narrow line to walk. You already knew this. Moderate exercise, good diet, they're there for a reason. They're the things that make you be healthier and keep your cells working better. Your cells can only divide so many times. It's the telomere issues, and it is for these guys too. And there's issues of what's called a Hayflick limit, which is every time a cell divides, it generally gets one genetic defect. And you can't have too many genetic defects before you have a problem. But look at this, look at what these things are. Osteoarthritis, osteoporosis, aged molecular macular degeneration, COPD, osteosclerosis, right? Diabetes. Your mitochondria there, and pay attention to them, because when I talk to you later, mitochondria in your human cell, your nucleus occupies some percent. The mitochondria occupy up to 3 times that. And that becomes important when you start beating up your cells for various reasons. So here's one that I picked, because I happen to know 2 people who have spinal cord issues. One in the upper back where it was fusing, and one in the lower back when it was an accident, and it cracked and broke the nerves, right? And has to walk around with braces or roller rotors again. The fact is, you can treat that now. You can take some pluripotent stem cells and make them into spinal cord nerve cells and inject them into the right places. Now, this is a site it should send shivers into you. Here are all the little pieces where they're growing, the little stem cells that are the reproduce. Why are they out in the open? Okay. This should be a completely automated thing, closed system where the human beings who are working on it and the machines that are making it, they're completely sealed from each other, so the person's not exposed and the stem cells are not exposed. But this is actually, it's a fixed up picture from an actual lab where people are doing this. It's very crude state in its stages these days doing this kind of sequence. But just like there are 4, actually +2, eye treatments with stem cells, it's the pre-stem cell ones and so on. There are a number of treatments for spinal cord issues, spinal cord and vertebrae issues. Let's look more at the process, because in the end, it is the process that you want to improve and make it safer and make it automated and reliable and cheap. We're making a product that we're going to give to 10 million people here in this island, set of islands. We want it to work well and be safe. Okay. We're using physics to cure cancer. I became convinced that the CAR T-cell approach is by far the best approach. And people that don't know what it is, you take your white blood cells and you take them away out of your blood and you save them to when you need them, and then you activate them, give the cells some information about the cancer, and then grow a whole bunch of those cells and inject 1 million of them back into the patient, and it eats the cancers. And even the ones that have metastasized off to the side, the goal is to get your T cells, the immune system cells, and preserve them for the 20% chance you're going to get cancer. And if you're older like me, your odds go up because most of the cancers go to 6 power of your age. The thing is, you want to store them and save them. When you get cancer, the 20% chance you would if you gave your stem cells what you should have, which was in your late 20s, early 30s, as opposed to the medical ones, because it's got to learn about what things it should be, attacking and not attacking. And then you unthaw them, and you select ones, and you activate them to have a gene that attacks the particular cancer you have. And then you do cell expansion, that is, you divide those cells into a whole bunch of times until you get up to 1 million cells. And then you preserve some of those for the second treatment, and the rest goes into the patient. It's not a perfect process because there are humans and stuff involved in it partly, but a lot of it is partly automated. So let's look at it a little more carefully. If we think about why this problem is the problem it is, okay, there's a huge amount of computer power and data handling. There's going to be way more math and AI involved in it, because you can already have the person's DNA. If it's their umbilical DNA, you can map that completely if you have the right tools. We're not quite there yet, but they're going to get there. And you can then make predictions of what things that person should be looking out for in their life and track them. There's a huge amount of things that are stochastic and environmental and so forth. And by tracking the person, you can make a prediction of which things they're likely to have problems with, be monitoring from that, and be ready to take their stem cells and make a fix. In 20 years from now, we can actually make whole organs. But that's a tremendous amount of stuff. If you're going to handle something on the scale of Hong Kong, you're going to want to handle on the scale of millions of stem cell batches, T-cell batches, and you have to track that data, you have to track the DNA, you have to do a huge amount of stuff. It's a huge data program, but if you can cross-link data, you can learn a lot more if you can follow whole cohorts. It's a longer-term view. There's a whole bunch of things that you want to do, but I mean, this drawing is kind of a simple drawing. It's going to require very huge data center and operations to monitor the quality and what's going on in the whole storage and the processing, but also to make models of the person and seeing what's going to happen, what their reaction should be, what's going to be going on. Here's the CAR T-cell stuff that I got in about a decade ago. Is convinced that the other approaches that I had were not as good as this. And even though this isn't physics directly, it is physics indirectly. So I got involved in consulting with Shanghai Cell to help design them a highly reliable liquid nitrogen cooling system. If a typhoon came or power outage came or whatever, they would still preserve all the cells and keep track, and have a way to keep track of everything. You get the blood, you separate out the T cells, you go through and select the ones you think that are good, right? And then you either freeze them and store them, or you modify them to genetically attack the particular kind of cancer that's going on. You expand them quite a lot, you put them back in the patient, and it eats their cancer. This is a different one. This is one of the things that I had done earlier to use physics and that was to use magnetic nanoparticles of the correct size. Because it turns out cancer tumors, blood cells are all kind of messed up and stuff. If you get above the regular size, if you get to a certain size, it can't go through the tumor. The magnetic nanoparticles, if you code, can't go through the tumor. They can go through normal vessels. So they collect in the tumors. So if you do magnetic resonance imaging, these tumors stand out like crazy. But if you also do that, you can use magnetic heating, that is, you can magnetic field flux, heat the nanoparticles. They're coated in a plastic. That plastic can also contain chemicals to kill cancers, and you release it in the cancer. The important part is concentrated. And then there are some people who went on and said, okay, we can do that, we just burn them. If we can collect enough of these magnetic nanoparticles together, we'll just use the magnetic field and we'll burn the cancer. Well, that's crude, but it's the earlier you detect the cancer and the earlier you treat it, the more likely the patient is to survive. So nanoparticles came back as a way to drag them through the tumors, get some of the biomarkers in the tumors, and then put it on the T cell and train the T cell to attack that. And you do the testing, and then you fly it to the patient, and you inject it. And the doctor or the nurse should be involved there, and a nurse or a doctor should be involved there. There shouldn't be humans in this part of the loop, or just in a very mild kind of way. This is the actual cell therapeutic line, and there should be in parallel DNA mapping, health protective systems. In engineering, they call it digital twin. In medicine, it's just beginning to make digital twins and stuff. But there should be a digital twin of you that you could run simulations on, and those simulations tell you the consequences of your life choices. So here's something that I did many years ago. I made up an error budget. And it was an error budget to say, if I were to measure signal from the birth of the universe, how accurately did I have to do it? How well did I have to make the detectors? How many switches and reveals and things I do? And there was a bunch of stuff like that. And for the satellite, I had one person whose job full-time was called systems engineer. His job was to keep track of the error budget to make sure that none of our parts and none of our things revealed that we had systematic errors that we couldn't remove. And it was very hard. So I looked at what the current rate is for good systems. How bad is the stuff incoming? Well, it turns out people don't handle those samples as well as they should. It's a 40% casualty rate to the cells going in. I think that should be around 2%, but we'll see. I think of ways to do that, but we'll see. There's a storage rate, and the thing that I seem to be the only person doing this kind of stuff is notice there is radiation, and radiation whacks storage stuff way more than you would think it would, because it's frozen. It can't fix itself. And that I wanted to get down to 1%. We can't do that yet, but I can give you paths which may get to that measurement. The removal and unfreezing error rate, which is around 2%, right? Because you've also got to make sure that you don't put somebody's cells in the wrong place. That you can't, that somebody doesn't drop it off of the 15th tier and smash it, right? There's a bunch of stuff you have to do to make sure of that. And you have to have an inspection. You can have an inspection error rate. Once you get to a low enough rate of errors and other stuff, the inspection error rate doesn't matter as much because you have fewer bad cells to have to deal with. And activated cell expansion error rate is high. You've got to go through and throw away 3/4 of the cells before you have a set that you can give back to a patient. That's really pretty terrible. The total loss of cells is almost 100%. It's not quite, because people are getting stem cell therapy, but there's a whole lot of intervention that has to be done, whereas I think it should be on the scale of 80%. That would mean you have less expansion to do because you have more cells to start with, and more are going to survive. And that's the goal, that 5 years from now you want to be doing this kind of thing. And there are some things that block it, some things that don't. So I call this an error budget table because that's what we used to call it back in the antique days when I was thinking, how can we be sure we can make this measurement? Here, it's how can we be sure we can actually produce cells safely and reliable in an automated way. Okay, so here's an example of expansion of human pluripotent cells. You picked out the ones that you want to culture. You've modified their genetic or their markers, and then you put them into a medium which causes them to grow and divide fast, roughly once a day. And so what happens? Every time the cell divides, it gets an error on average, not every one. You will find that if you're going to divide them 20 times, there's going to be a number of errors in that kind of stuff. You need them because if you might be going to die from the cancer, you prefer to have some bad cells than to have a cancer. What happens is, if it gets a mutation that makes the cell grow faster in the culture, you'll get a lot more of those cells. It's simple math, right? It's, kind of. So when you have an extended culture, you end up with a few of the cells that are pretty much like the original, and a lot of cells that grow faster and have some other kinds of things. But some of them are going to die because their mutations were bad. Right? So you need to figure out, how can I make that a more stable situation? There's probably not much we can do. The hay filament's been around for a long time. Nature has a lot of tricks and things to do. So when you're in vivo, like in our bodies, a lot of those errors get fixed. Here, you're growing really fast and you're going to sort them and inject them into people. So you want to find a good way to try and handle that. If you're looking to up to 25 divisions, you're going to have some problems. You've got to figure out how to handle that in an efficient and effective way. And you're going to want to look at them and see, genetically sample some of them to see if they're doing okay. And also realize their telomeres have probably gotten shortened. These are T cells, but they're not brand new T cells, they're slightly used T cells. But they're going to help you out of your problem. Okay, what's wrong with this picture? People are in it. That's the mistake. And they got a rolling cart, but they should be super clean. Her hair shouldn't be out like that. It's a lot of other stuff. But this is a real picture. I have some other pictures that I took like a Shanghai cell and in Bohai, and Bohai cell has something. There are rows like this of these things that contain frozen cells. Right? They're all lipid management. If you look, they're gravity fed. There's lots of things that people do semi-standard now. But you also going to want to have in your stem cell factory, when the stem cell is taken out by a machine and put into the right place, you take out a sample, and that factory goes to work on it and makes it. Right now, you have humans intervening in various steps to try and check something. That's a mistake. Right? And here's another example of my archive. But when you start thinking about this, this is a pretty big deal. Right? So here's an ad. So one's on the right or for the ad, one's on the left or one of their competitors from a higher company. Okay, so what is going on here? This one is a relatively small one, like that. It's a big liquid nitrogen cooled tank, a nitrogen atmosphere in it. There are lots of stem cell samples at each of these columns, and you can send a command by computer. It rotates around and raises the stack up so the robot arm can reach in and take the stem cell and take it over to the factory. This is the beginning of what it's going to take to automate the automated stem cell factory. Now here's my first attempt using AI to make a picture of the thing I envisioned based on what I calculated. And I wrote these words, and I used the AI, and it sent me back this, and I described it all, and this is the picture it gave me. So imagine this is from the view out from the left here, except they put a bunch of student dorms and stuff like that. And here's another one where I tried to say it's okay. And it put plants there. It's got to be sterile, it's got to be clean, and it doesn't have to be outside. The solar, these guys should be inside shielded, not outside like this. And then finally, this is one I did with DALL-E, and it got some stuff right. It doesn't have any solar panels. It doesn't have the liquid nitrogen stuff on the top, but it shows you the kind of scale where I want tanks like that are storing on the scale of thousands to tens of thousands of samples, stem cell samples frozen. And then I need to be able to access them robotically, and then I need to be able to do that. And over time, things are going to change. I need to be able to get in here and take pieces out and put new ones in, etc., without disturbing the whole system. This is the scale kind of thing you have to think about. If you really want to do all 10 million people, you need 1,000 of those tanks. Plus you need the factories. This is what you want to get to eventually. Right? So this is my weak AI attempt, because AI is trained to make things like other images that it sees, not like what you're telling it. Here is an idea what kind of cells are in your body. So this one in the middle, how many cells you have by number. A lot of what you have is blood cells. So it's not surprising that a lot of stuff is done with blood cells. Now, one thing that isn't shown here, there are 4 times as many cells that are red blood cells without nucleus. Okay, so you don't show them on this chart. Everything else you do, right? But there's nucleated red blood cells, which you don't usually pay attention to. But there's a whole bunch of different kinds of white blood cells. And when I first started looking at this years ago, they didn't know what NK cells were. NK is short for natural killer cells. There's some part of the cell, the immune system cells that are just naturally kill things it doesn't know about. Right? Sometimes it attacks you, but mostly it's the thing that attacks your cancers or other things that some people have very well, and that lasts pretty well. So if you look on this plot, cell mass versus number goes down as almost the first power, right? What's that telling you? There's roughly equal mass of every scale size of cells. It's just kind of funny. You know, why is that power? Well, I haven't figured that out, but I'm sure there's a reason why the body does that. But in terms of total mass, a lot of your mass is in your bones. No surprise, you know this, right? I'm not sure, I mean, it's a structural issue as opposed to a cellular machine function issue. And there are lots of different kinds of cells. So the relevant question here is, what's the size of the typical human cell that we want to deal with? Here's the micrograph that shows HIV, it's a virus, a T cell, typical size of a T cell, and a bacteria. Bacteria is about 1 micron. This is on the scale of 7 microns. I usually use a round number of 10. HIV is 10th of a micron. It's very small. But you look up there and you can see the different kinds of ones, and they run from 7 microns up to 18 microns. So it's typical kind of scale size for the things we're going to be dealing with. Except there's one special kind of cell, which is human eggs. There are mitochondria, and there's single-strand DNA. And single-strand DNA is very vulnerable to disruption by radioactivity. So if you're going to do it, it's better to fertilize if you're going to do storage, right? And because you have double strand, and it's only neutrons that really consistently break double strands and ruin them. So, but if you take an egg like this, it's big, it's 120 microns. That means its chance of being hit by radiation is roughly 100 times that of your T cell or a bunch of other of the stem cells. And it will do a lot of damage to the nucleus, and it will do significant damage to the mitochondria. So they should be stored in very low reactivity places. That's one of the things that I realized when I was doing, which is we're getting to. So apparently I'm one of the few people that realized that frozen cells and in vivo cells react very differently to radiation. Storing cells
But what he was using was large sheets of plastic, which are good insulators, just like completely frozen minus 190. Electrons don't move around very much, that's why they can stay preserved. So when you have ionizing radiation come through, the electrons just wander off and they don't come back. And you have the broken thing going until you thaw them out. And so there's an issue. And so if you do the order of magnitude calculation, there's roughly 1 muon per 60 seconds per square centimeter. And you multiply that up to the number of square meters, the 10 to the fourth, you get 100 muons per second going through a square meter. One of these things is 10 microns on the side. So a year, you're going to get on the scale of 1 hit. Every cell is going to get hit by a cosmic ray muon every year. You want to store it for 10 years or 100 years? Because of the lack of diffusion, because of other things, the damage to frozen cells, I calculate, should be significantly worse. And I did it several different ways. And because of that, I started looking at all the background radiation doses, just to show you. The cosmic rays, about 1/3 of a millisievert per year. There is a number of spectrals, which is the number of decays per second. There's the number of hits per second. There's the number of, and so on. Sieverts are weighted by biological damage. This is done from the old days when they were worried about radiation effects on humans, live humans, right? Cosmogenic ones, we'll skip over that, but there's some stuff produced in the atmosphere by the cosmic rays that you end up breathing into. We're getting exposed to about 0.2, perhaps a little more, but we get a little more cosmic rays, just from the rocks. And we inhale a lot. That's because there's uranium and thorium chains that are giving out radon, and the radon gets trapped in a room like this, and you breathe it, and it's fortunately, unfortunately, mostly alpha particles, which means it mostly stays in your lungs. That's why you get lung cancer. That's why you want to have your house and your office ventilated reasonably well. In your own body, there's also radiation. I'll get to that in a second. The total is about 3 millisievert. So cosmic rays are only 10% of it. So here are the backgrounds again in a different way. The radon, in terms of radiation dose to you, is huge. The thorium and uranium lines, they're only about 4%. The cosmic rays, 11%, terrestrial 7%. The radon-220, as opposed to 222, is about 5%. Those are the sources of radiation that exist. If you wanted, you've got to protect, store stuff from that. Here's a big one, because when I first did the calculations, I thought we could do about a factor 10 better than we can unless we figure out how to solve this problem. You're hot, and you're radioactive. And so it's an issue that you're radioactive because the primary radioactive in humans is calcium-40, which has a lifetime of about 1.2 billion years, and it's only 0.01% of the calcium in your body. Your body cells use calcium very, very much because it's a conduit to signal and do other things. That means if you're a 70 kilogram person, you're having about 5,000 becquerels, which means you have about 5,000 decays a second in you. It is, in the time it took me to say the sentence, you had more than 10,000 decays in your own body. Now, fortunately, most of those decays don't do damage to the person who's sitting next to you. It's the ones that give out the gamma rays and so forth. But the carbon-14, which you're breathing in all the time, eating in all the time, you're adjusting it in various ways. Carbon-14 gives you 3,000 decays a second. Fortunately, it's almost all beta rays, and they do simpler damage to the body. So their sieverts order of magnitude less than you would have thought in comparison. You got rubidium, you got tritium. These are mostly from the nuclear tests done by the US, well, the Soviet Union, the US, and China, and that's residual in the atmosphere. But here's an interesting picture of beta rays. Do you recognize what this is? It's a banana. Okay? If you eat a banana, it's 1% of your daily dose of radiation. Okay? This is a pork chop. This is, I think, some citrus, some various things like that. almost everything that you ingest is radioactive. It's hard to get away from that. You've got to think about how to carefully choose your cells so you can minimize the potassium-40 decay. Radiation damages chronic reserve cells. And I searched through the literature for a long time till I finally found one article that dealt with this. All the articles that exist deal with in vivo radiation exposure, except this one. I mean, I searched through a lot of literature. I actually had a colleague use the university, because I was out of town, use the university, special system to do extra searches. And this is the only one that I found. And this is just shows you what kind of radiation you gotta worry about. Okay, here's what they found. It's not a perfect article, but at least there's some data. So these French people did exposure to chronic reserve cells at 2 months, 5 months, and 7 months. Not very long time, but they did it in an interesting situation. Level 1 was at their lab in France. It was below a 6-story building, and it was 2 more stories underground, and a low radiation environment and low radiation equipment. The radiation background was about 10% of what you get here at sea level, here near sea level, right? And this is how many cells came out, roughly 7%, plus or minus 2. It came out looking damaged. Now, they also then went to Grenoble, to the top of a building, and they took the stuff and exposed it on top of sandbags that had some thorium and other stuff in it. So the cosmic rays were higher, and the gamma rays from the thorium were higher. So they got roughly 10 times the dose. And you will notice they got up to about 16% of the cells being affected so bad that they died. Then they went deep underground. It's a deep underground facility, which has lots of shielding, uses low radioactivity metals in containers, and has cement that's radiation shielding. They have special material. And so they got to a dose which is way under the 10%. It's less than 1%. It's probably about a 10% of what it would be. And they got this kind of range for the answer. Now, there's lots of things about this paper that I don't think is perfect, but this is the only data we have. And it kind of is in the right range for my calculations, but it isn't perfect for what we would know. We'd like to know for longer term. If you did for longer time periods, the effect would become more dramatic. And at least they went to a somewhat protected area, to 10-meter water equivalent, and the IR in the mountains, a kilometer up, so they got 3 times as much cosmic rays, and then they put sandbags with thorium gamma ray producers in it, and put the stuff on top of those, so it was getting the stuff from both sides. And there was an effect. Now the question is, how good is this result? When you read the paper, it's a little complicated to read, but it seems like they did reasonable stuff, but you'd like to have more stuff, and you would like to have a procedure that didn't have all those extra deaths, right? Because this guy could be way down here if it wasn't for the other things that cause the cells to die. Now, that caused me to do 2 things. If you look at this, the Earth has a magnetic field. That Earth's magnetic field turns high energy cosmic rays around and sends them back, but not high enough, pretty high energy ones. So if you look at the place at the North Pole, the South Pole, magnetic poles, you get a lot of radiation coming. If you look along the magnetic equator, it's much less. The minimum, because it's slightly offset from the center of Earth, the minimum happens to be in southern India and Thailand. So it means if you're flying your samples into Thailand, all because you have lower background radiation coming into your samples, even in that short-term manner. But a lot of the mines in Mexico are highly radioactive. You've got to vent them to get the radon out. You've got to do a bunch of other stuff. And so it's not super cheap to do that. For various reasons, I believe in a horizontal access rather than a vertical access. So investors want to be in this, and we put a proposal in to the Mexican NSF to try and get this. So the expectation is we'll be doing a study and we'll be doing that because there are enough rich people in Mexico City they will pay to store their stem cells and their T cells, you know, even if the average population doesn't get it. In Mexico City, it's 20 or 40 million, depending on how you draw the box around it. There's a big set of people who do that. And it would be good for Mexico to have stem cells that were robustly made and cheap so that more of the population can afford it. So we're making progress there, more so than I like, because it's being driven by the financial people. People want to make a bunch of money from it, more than by the scientists. We'll see what happens. If you think about what has to happen, you got to think about designing it as an engineering production design problem with some scientific questions that need to be fixed. We need a couple of physicists working on it, a couple of chemists, a few bioscience guys, but mostly engineers, because this is a production engineering design problem. How do you set the thing up so that as time goes on, you can automate it more and more until you're really the Dell computer of stem cell processing? And since we're putting stuff in people, there are going to be regulatory compliances to prove that you're monitoring this whole process and that you're putting quality products into people. And that, I think, is a good thing to do, but it requires extra over the normal building products kind of device. Here's my conclusion. We have some research and some design to be done, that a university is the real place to do it. We just have to think, how do you put together a team that can make that? And I predict a good fraction of people in this room are going to want to use the stem cell therapy for something. But it's great also, it gives you a job, gives you a reason to keep being here. So thank you.